Welcome to solverfy.
.68. So strontium-90 is produced in nuclear fission reactions, both in fission reactors and in atomic bombs. So we wanted to look at where it is in the periodic table to look at what elements it might be similar to chemically. The elements in one column of the periodic table generally tend to have similar chemical properties. Then we want to figure out why that might make it bad to ingest it. And so it decays. It's also radioactive. So it decays with a half-life of about 29 years. And so we want to figure out how long it'll take for a sample of yttrium to get to 1% of its current level. In this particular case, it's phrased as the amount on the surface of the Earth. And then we also want to write down the decay reaction, and including the daughter nucleus, which is also radioactive, and we want to write down what its decay is. So to begin with, strontium is in the same column as calcium. And your body is pretty good at storing calcium. So part of what your bones do, in addition to being actual structural elements of your body, also store part of the calcium that they're made out of is sort of a storage of calcium, because it gets used in ion form for things like neurons and muscle cells and stuff. So that's bad, because that means that the strontium might well be stored in your bones, and then it's radioactive, and it's fairly short half-life, so it's not likely to be a good thing for you. Also, it's possible that something might go wrong with the uses the body uses for calcium. Strontium might screw that up somehow. Who knows? I mean, I'm sure this is known, but we're supposed to try and figure this out, just based on the periodic table here. So now the time that it needed to get to 1% of its original level, 0.01 of n over n naught, is going to be e to the negative lambda t, so we want t here. So solving for t and substituting in log of 2 over the half-life, so that we have this in terms of the quantity that we know, we get that the time is going to be the half-life over log 2 times the log of our 1%. And so that will take 200 years. Now, we're told that strontium has too many neutrons. So it's probably going to undergo beta decay, so that some of the neutrons get turned into protons. So we imagine then that the charge number goes up by 1. The mass number stays the same because the number of nucleons hasn't changed. And this is yttrium-90. And we also get, of course, the beta and the antineutrino. And then the yttrium-90 probably still has too many neutrons. So it's going to undergo another beta decay. So the mass number remains unchanged, but now we get another proton in the nucleus. And element 40 is zirconium. And then, of course, you get the beta and the antineutrino.